Io is melting alive. Every other world in the solar system that looks like Io should be long dead by now. A body this small, roughly the size of our own moon, should have cooled off billions of years ago, gone quiet, and frozen into another cratered rock drifting through the dark. That's how it works. Small worlds lose their heat, their cores go cold, their surfaces stop moving, they become corpses. Io didn't get that memo. 4 billion years into its existence, this moon is still tearing itself apart from the inside out. Its surface is an erupting wound, covered in over 400 active volcanoes that fire molten rock hundreds of kilometers into space. Not occasionally, constantly. Io is the most volcanically active body we have ever found in the solar system, and it isn't even close. Nothing else compares. Not Earth with its tectonic drama, not Venus with its resurfaced plains. Io makes every other geologically active world look like it's sleeping. And the thing that keeps Io in this state of permanent destruction isn't some internal furnace or leftover radioactive heat. It's Jupiter. The same gas giant that shaped the architecture of the entire solar system is also, right now, at this very moment, squeezing one of its own moons like a stress ball until lava bleeds out. To understand why Io exists the way it does, you have to understand the trap it's caught in. Io orbits Jupiter at a distance of roughly 422,000 kilometers. That sounds like a lot until you realize Jupiter is so massive that its gravitational influence at that distance is overwhelming. Io completes a full orbit in just 42.5 hours, racing around its parent planet faster than most moons in the solar system. But speed isn't the problem. The problem is that Io is not alone in that orbital neighborhood, and the company it keeps is slowly killing it. Europa and Ganymede, two of Jupiter's other large moons, orbit farther out. Their gravitational pull tugs on Io in a rhythmic pattern that locks all three moons into what physicists call an orbital resonance. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This sounds elegant, almost musical, but for Io, the effect is brutal. Europa and Ganymede keep nudging Io's orbit into a slightly elliptical shape, which means Io's distance from Jupiter is constantly changing by a small but critical amount. When Io swings closer, Jupiter's gravity squeezes it harder. When it drifts farther away, the squeeze relaxes slightly. Then it swings back in. Squeeze, release. Squeeze, release. Every 42 hours, forever. This is tidal heating, and on Io, it generates somewhere between 60 and 80 trillion watts of energy. That is roughly twice the total energy output of every power plant on Earth combined. All of it being pumped directly into the interior of a moon roughly 3,600 kilometers across. Think of it like kneading a ball of dough over and over without stopping. The friction generates heat, except the dough is rock. The hands doing the kneading belong to the largest planet in the solar system, and the process has been running non-stop for 4 billion years. The rock inside Io doesn't just warm up, it melts. Beneath a thin crust that can't be more than 30 to 40 kilometers thick in most places, Io likely has a global ocean of magma. Not water, not ice. Liquid rock, hundreds of kilometers deep, churning under a surface that keeps cracking open because the pressure below never stops building. Thermal models suggest this magma ocean could extend down 50 kilometers or more beneath the crust, which means Io's solid shell is essentially floating on a sea of molten silicate. The ground isn't ground. It's a lid on a pot that's perpetually boiling over. There's a detail about the tidal heating that's easy to miss if you're not paying attention to the geometry. Io is tidally locked to Jupiter, the same way our moon always shows one face to Earth. That means the same hemisphere is always pointed toward Jupiter, and the tidal bulge, the physical deformation of Io's shape caused by gravity, is always centered on roughly the same spot. But because the orbit is elliptical, that bulge grows and shrinks as Io moves closer and farther from Jupiter. The crust flexes. It cracks along those flex lines, and those cracks become volcanic vents. Scientists have noticed that Io's volcanoes are not randomly scattered across the surface. They cluster in patterns that correlate with predicted zones of maximum tidal stress. The geology is a map of the gravitational torture being applied to it. You can read Jupiter's grip in the arrangement of Io's eruptions. If you could somehow stand on Io's surface in a suit that magically protected you from the radiation, the cold vacuum, the sulfur dioxide frost, and the eruptions happening in every direction, you would be standing on a world that looks like nothing else humans have ever seen. The sky would be black, no blue haze, no scattered light, just the hard vacuum of space pressing down on a landscape of frozen sulfur stretching to the horizon. Jupiter would dominate your view, filling roughly 40 times more of the sky than our moon does from Earth, a swirling wall of orange and brown bands hanging above you in permanent silence. You wouldn't hear the eruptions. Sound needs atmosphere. On Io, volcanoes erupt in absolute quiet. You'd see a column of material launch silently into the black sky, arc outward, and fall back to the surface without a whisper. The most violent volcanic world in the solar system operates in total silence. There are no impact craters, not because Io has never been hit. It orbits inside the most crowded gravitational well in the solar system, but because the surface is replaced so quickly that craters don't survive. The entire face of Io resurfaces itself at a rate of roughly 1 centimeter per year, burying everything. A crater that formed 1 million years ago is now under 1 kilometer of volcanic deposits. For context, the oldest surface features on our moon are over 4 billion years old. On Io, nothing lasts. The ground you'd be standing on might be younger than your car. The landscape would be alien in the most literal sense. Io is painted in shades of yellow, orange, white, red, and black, all of it sulfur and sulfur dioxide in various chemical states. Some regions look like frozen lakes of brimstone. Others are dark, fresh lava flows cutting across plains of sulfur frost. Towering mountains, some reaching over 17 kilometers high, taller than anything on Earth, jut up from the surface at odd angles. These mountains aren't volcanic, they're tectonic. Massive blocks of crust shoved upward by compressive forces as the surface continuously folds and buckles under the stress of all that internal activity. Mount Boussole, the tallest confirmed peak, rises roughly 17.5 kilometers above the surrounding terrain. Everest, by comparison, stands at just under 9 kilometers. Io builds mountains the way Earth builds anthills. Volcanic calderas called patere dot the surface between those peaks, some of them wider than 200 kilometers, their floors glowing with magma that sits close enough to the surface to be visible from orbit. Loki Patera, the single most powerful volcanic feature in the solar system, is a lava lake roughly 200 kilometers across that periodically resurfaces itself in massive overturn events. The mechanism is similar to what happens when a skin of cooled lava on a lake gets heavy enough to sink, dragging the crust down and exposing fresh magma beneath. When Loki flips, the thermal output spikes so dramatically that telescopes on Earth can detect the change from over 600 million kilometers away. An eruption on a moon of Jupiter, visible with ground-based instruments from here. That's the scale we're dealing with. And then there are the plumes. Io's eruptions don't behave like anything on Earth. On our planet, volcanoes erupt into a thick atmosphere that slows, cools, and contains the ejecta. Io has almost no atmosphere to speak of, just a thin, patchy envelope of sulfur dioxide that collapses and refreezes on the night side. When the sun sets on a given patch of Io, the sulfur dioxide literally freezes out of the air and falls as frost. When the sun rises, it sublimates back into gas. The atmosphere itself is seasonal, regional, and barely there. So when a volcano erupts on Io, the material launches directly into vacuum. There's nothing to stop it. Plumes from Io's most violent eruptions have been observed reaching altitudes of 300 to 500 kilometers above the surface. Pele, one of Io's most famous volcanic centers, produces a plume ring of sulfur deposits over 1,200 kilometers in diameter. That's larger than the distance from New York to Miami, and it's just the fallout zone from a single vent. Some of these eruptions are what volcanologists classify as outburst events, sudden, massive explosions of lava and gas that can change the appearance of Io's surface in days. In 2001, the Galileo spacecraft observed a fresh eruption near Io's North Pole that produced a lava flow covering an area of roughly 1,900 square kilometers in a matter of weeks. That's the equivalent of paving over the entire city of London with molten rock before anyone could file a complaint. And Io does this routinely. Monitoring campaigns using adaptive optics on the Keck and Gemini telescopes in Hawaii have caught dozens of these outburst events over the past 2 decades, each one temporarily doubling or tripling Io's infrared brightness as seen from Earth. The moon flares like a warning light and then settles back down, and nobody on Earth notices because we're not looking up. The temperatures involved are extreme even by volcanic standards. Most of Io's eruptions produce lava at temperatures between 1,000 and 1,200 degrees Celsius, consistent with basaltic composition similar to what you'd find at Hawaii or Iceland. But some eruptions have registered temperatures above 1,600 degrees Celsius. For a while, those readings baffled scientists because they were hotter than any known basaltic lava on Earth. The best explanation is that some of Io's magma is ultramafic, a type of lava so hot and fluid that it hasn't existed on Earth's surface in billions of years. The last time anything like it erupted here was during the Archean Eon, when our planet was young and its mantle was still a furnace. Io is erupting with the lava of ancient Earth right now, in real time. What makes this more disturbing is what all that volcanic activity is doing to the space around Io. Every eruption vents sulfur, oxygen, sodium, and other materials into Io's almost non-existent atmosphere, and most of it escapes immediately into Jupiter's magnetosphere. This creates a structure called the Io plasma torus, a donut-shaped ring of charged particles circling Jupiter along Io's orbital path. The torus contains roughly 1 ton of new material every second, all of it ripped from Io's surface and interior. Io is bleeding into space, and Jupiter is catching the blood. That plasma torus feeds directly into Jupiter's radiation belts, and this is where Io's neighborhood goes from hostile to genuinely lethal. Jupiter's magnetosphere is the largest structure in the solar system, stretching tens of millions of kilometers in every direction. And the radiation it traps near Io's orbit is among the most intense anywhere. An unshielded human at Io's orbital distance would absorb roughly 3,600 rem of radiation per day. A lethal dose for a human being is around 500 rem. You'd receive enough radiation to kill you several times over before a single day had passed. Even inside a heavily shielded spacecraft, the exposure would accumulate fast enough to cause serious damage within weeks. The Galileo spacecraft, which studied Jupiter and its moons from 1995 to 2003, had its electronics progressively degraded by radiation exposure near Io, despite being hardened for exactly this environment. Its tape recorder malfunctioned, its camera resolution deteriorated. Several instruments failed entirely over the course of the mission. When NASA finally sent Galileo plunging into Jupiter's atmosphere in September 2003, the spacecraft was already half blind. And even that death was deliberate. NASA destroyed Galileo on purpose to ensure it would never accidentally crash into Europa and contaminate a world that might harbor life. Io, meanwhile, got no such protection. Nobody worries about contaminating Io. There's nothing there to contaminate. Io doesn't just destroy itself, it poisons everything nearby. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, made its closest flybys of Io in late 2023 and early 2024, passing within roughly 1,500 kilometers of the surface. The images it returned are the sharpest views of Io since Galileo, and they confirmed what scientists had suspected for years. Io isn't slowing down. The volcanic activity hasn't diminished. New eruptions were visible, new surface changes were documented, and the lava lake at Loki Patera appeared to be in the middle of yet another overturn cycle. Juno's instruments also detected evidence that Io's volcanic output might be even higher than previous estimates suggested. This moon isn't winding down. It's as active today as it was when Voyager 1 first caught a volcanic plume in 1979. A discovery so unexpected that the imaging team initially thought it was a processing artifact in the data. That 1979 moment deserves a pause, because it fundamentally changed how we think about geology in the solar system. Before Voyager 1's flyby of Io on March 5th of that year, the assumption was straightforward. Geological activity requires internal heat. Internal heat comes from radioactive decay, and radioactive decay is proportional to the size of the body. Small worlds cool fast. Small worlds go dead. Io is small, therefore Io should be dead. Navigation engineer Linda Morabito was processing Voyager 1's departure images of Io when she noticed a bright, umbrella-shaped feature extending off the moon's edge. It was a volcanic plume, 300 kilometers high, erupting in real time. Stan Peel and colleagues had actually published a paper predicting Io's tidal heating just days before the flyby, one of the most perfectly timed predictions in the history of planetary science. But seeing it, actually seeing a world that small erupt with that much violence, rewrote the rules. Tidal heating became a legitimate geological engine, and suddenly, every moon orbiting close to a gas giant became a candidate for hidden activity. Europa's subsurface ocean, Enceladus's water plumes, the potential interior warmth of Titan. All of these lines of inquiry traced directly back to what we found at Io. Io gave us the key to understanding that oceans and geological engines could exist in places the sun barely touches. 4 months after Voyager 1, Voyager 2 flew past Io and confirmed that the eruptions were ongoing. The plume at Pele had shifted. New surface deposits were visible where none had been before. In 4 months, Io had already redecorated. When Galileo arrived at Jupiter in 1995 and began systematic observations over the next 8 years, the picture only grew more violent. Galileo detected over 160 active volcanic centers and watched in real time as eruptions reshaped entire regions. One flyby caught a fresh lava fountain on the surface so bright that it overloaded the spacecraft's near-infrared detector. The instrument wasn't built to handle something that hot at that distance. Io broke the thermometer, and it paid for that revelation with its own body. Io has no water. Whatever water it might have once held was driven off eons ago by the same volcanic activity that makes it scientifically valuable. There are no subsurface oceans, no potential for biology, No sheltered environment where chemistry could quietly complexify into something interesting. Io is a world that has been cooked from the inside for so long that anything delicate was destroyed before it ever had a chance. Europa gets the astrobiology headlines. Enceladus gets the mission proposals. Io gets nothing except more lava and more radiation and more slow, grinding destruction from a planet that will never let it rest. And honestly, that's the part that gets me. We owe so much of our understanding of icy moon geology to Io's suffering, if you can call it that. And yet, there are no plans to go back. Not really. The Io Volcano Observer, a proposed NASA Discovery-class mission, has been in concept development for years. It would orbit Jupiter on a trajectory designed for repeated close flybys of Io, mapping volcanic activity, measuring heat flow, and characterizing the magma ocean. Every time it comes up for selection, it gets passed over in favor of something else. Io doesn't have the astrobiological appeal that sells missions to Congress. Nobody is going to find life there. There's no water to protect, no organics to study, no biosignature to chase. So it keeps erupting, and we keep watching from a distance. And the most geologically active world we know of remains one of the least explored. There's a question that doesn't get asked enough. What happens next? Not next year, not next decade. What happens to Io over geological time? The tidal heating that drives its volcanism is slowly transferring orbital energy out of the system. Io is gradually spiraling inward, closer to Jupiter, fraction of a millimeter by fraction of a millimeter, over hundreds of millions of years. The closer it gets, the stronger the tidal forces become. The stronger the tidal forces, the more violently Io erupts. The more it erupts, the more mass it loses to the plasma torus. This is not a stable arrangement. It's a death spiral in slow motion, playing out over timescales so vast that it's invisible to us, but absolutely inevitable in the math. Eventually, hundreds of millions or billions of years from now, Io will cross the Roche limit, the distance at which Jupiter's gravity exceeds the internal strength holding Io together. When that happens, Io won't collide with Jupiter. It'll be pulled apart, stretched and shredded into a ring of debris orbiting the planet that tortured it for billions of years. Sulfur and silicate and iron, the guts of a moon that spent its entire existence being squeezed to death, spread into a thin band circling Jupiter's equator. Saturn has its icy rings. Jupiter would get a ring of volcanic ash and molten shrapnel. Jupiter will wear Io's remains like a trophy. There's something almost personal about it. Jupiter didn't just capture Io. It didn't just trap it in a resonance with Europa and Ganymede. It kept it close enough to break, but not close enough to kill quickly. Io has been in this arrangement for billions of years already, billions more to go before the end comes. That's not destruction, that's patience. That's the future of the most volcanically active world we've ever found. Not silence, not peace, dismemberment. And until that day comes, Io will keep erupting. It will keep bleeding sulfur into space, keep resurfacing itself, keep glowing in the dark with the heat of its own slow destruction. No other world in this solar system works this hard to stay alive, and no other world is being punished this relentlessly for the crime of orbiting too close to something too massive. Io isn't just a moon, it's a warning. Every world pays a price for the orbit it keeps, and some prices never stop being collected. Thanks for watching, and I'll see you in the next one.